Why is the geometry, cone volume formula 1 3 pi r squared h? Have you ever wondered why the formula for the volume of a cone is 1/3 times pi times the radius squared times the height? It might seem puzzling at first, but let's break it down together. To start, let's consider the shape of a cone. The base of a cone is a circle, and the area of that circle is calculated using the formula pi times the radius squared. The radius is simply the distance from the center of the circle to its edge. Now, the height of the cone is the straight line from the base to the tip, or vertex, of the cone. When we think about the volume of a cone, we need to compare it to a cylinder. A cylinder with the same base and height has a volume calculated by multiplying the area of the base by the height. So, the volume of the cylinder is pi times the radius squared times the height. Here's where it gets interesting. If you were to fill a cone with water and pour that water into a cylinder of the same base and height, you would find that it takes exactly 3 cones of water to fill the cylinder. This practical observation shows us that the cone occupies 1/3 of the space of the cylinder. Mathematically, this relationship is confirmed through a method called integration, which is a part of calculus. By slicing the cone into very thin disks and adding up their volumes, we find that the total volume equals 1/3 times pi times the radius squared times the height. So, when we look at the formula 1/3 times pi times the radius squared times the height, we see that the pi times the radius squared gives us the area of the circular base. The height represents how tall the cone is. The 1/3 factor accounts for the cone's tapering shape compared to the full cylinder. This formula is essential in geometry, especially when calculating how much space a cone occupies. It has practical applications in various fields, including engineering and architecture, where conical shapes are common. Understanding the volume of a cone helps us in real-world situations, such as when designing conical containers or structures. So next time you see a cone, remember the fascinating math behind its volume.